Welcome back to AI.Code.Cast. Today we're tackling the classic problem of reversing a specific portion of a singly linked list.
Yeah, it's a real brain teaser that comes up pretty often.
Definitely. And as we'll see, the solutions are pretty elegant when we start to consider efficiency. But before we get into the nitty-gritty, can you give me a quick reminder about singly linked lists? What makes them so tricky to work with in this context?
Sure, a singly linked list is kind of like a one-way street. You can only go in one direction, from head to tail.
Right.
Each element, each node has a pointer to the next one, but there's no going back.
Ah, I see. So if we want to reverse a section in the middle, it's not as simple as just like backing up and rearranging like we could with an array.
Exactly, you hit the nail on the head. That's what makes this problem so challenging. We have to be really strategic about how we change the links between these nodes if we want to reverse a section without, breaking the whole chain.
Okay, so to make this a little more concrete, let's add some constraints. Let's say we have a list of up to 500 nodes, and each node can hold an integer between, say, -500 and 500.
Okay.
And then we're given two indices, left and right, which tell us the start and end of the section we need to reverse.
Got it.
So our goal is to reverse the order of the nodes within that specific section, leaving the rest of the list as it is.
Makes sense.
So where do we even start with something like this?
Well, I always like to start with the simplest approach, even if it's not the most efficient.
Yeah, that's good strategy.
Just to kind of wrap our heads around the problem before we get into anything too fancy, what do you think would be the most intuitive way to reverse a section of something, just in general?
I guess if I were just thinking about rearranging things, the easiest way would be to take the elements out of order, set them aside, and then put them back in. But, reverse.
Yeah, exactly.
Could we apply that logic here?
Absolutely. That's pretty much the brute force approach. We could copy the nodes from that left position to the right position into a separate data structure, something where reversal is easier, like an array.
Ah, that makes sense.
Mm-hmm.
With arrays, we can access elements directly by their index, so swapping them around to reverse the order is easy peasy. Then we just copy those reversed elements back from the array into the linked list.
Yep, you got it.
So this brute force method seems pretty straightforward, but there's got to be a downside, right?
Yeah, there is. You're right. There's always a trade-off. The big drawback here is the extra memory we're using to store that array.
See.
The larger the section we're reversing, the bigger the array gets. And of course, the more memory we consume.
So if we're talking about like massive linked lists, this approach could become really inefficient.
Exactly. It might be fine for small lists, but if you have millions of nodes, that extra memory usage can really become a bottleneck. This is where the idea of space complexity comes in. It's basically how much additional memory an algorithm uses.
So, the brute force approach, while it's easy to understand, it's not great for memory efficiency. Is there a way to reverse the section directly within the linked list itself without needing that extra storage?
You're thinking like a true coder. And yes, there is. That's where things get really clever. We can actually do what's called an in-place reversal. And that means we're just manipulating the pointers within the linked list.
In place, meaning we're not making any copies,
Right.
no temporary arrays. We're basically rewiring the connections between the nodes on the fly.
Exactly.
I'm intrigued, but also a bit intimidated. Pointer manipulation can be hard to get your head around sometimes.
It definitely is. You have to think about things differently. Yeah. But the logic is super elegant once you see it.
Okay, I'm willing to give it a shot. Where do we start?
So to make this more concrete, let's imagine we have a few key pointers. Let's call them prev, cur, and third.
Okay, 3 pointers.
Think of them as your helpers, kind of navigating through this list.
Okay, I'm picturing them like little flags marking different positions in the list.
Eh.
What role does each one play?
So cur is pointing to the node we're currently working with. Prev points to the node before cur. And then third is pointing to the node after cur.
Okay.
They basically work together like a little synchronized team to reverse these links.
I'm visualizing it, but I still need a little bit more to really grasp it.
Sure.
Can we maybe go back to that train analogy to illustrate how these pointers move and change things?
Okay, yeah. Let's say we have a section of train cars we want to reverse.
Okay.
Imagine cur is like a person standing at the start of that section.
Okay.
Prev is behind it, and third is like one car ahead.
Got it. They're positioned around the section we want to reverse.
Exactly. Now, third kind of uncouples the car it's at, and then cur links its car to the one behind prev, reversing that connection. Then They all move forward one position.
Ah, I see. So it's like they're systematically uncoupling and recoupling cars, and as they move down the line, they're reversing the order.
You got it. They just keep doing this little dance until that whole section is reversed.
That is a really helpful way to visualize it. So
Hmm.
in our linked list, these pointers are essentially doing the same thing, but instead of physically uncoupling cars, they're changing the next pointers of the nodes.
Exactly. Each node in a linked list has that pointer called next that tells us which node comes after it.
Right.
And so by updating these next pointers, we can effectively reverse the order.
Okay, so I think I'm getting the basic idea, but how do we make sure these pointers are moving correctly? It seems like there's a lot of room for error here if we're not really careful.
You're absolutely right. Precision is super important when you're working with pointers. We need to make sure they're initialized correctly and then updated in the right order as we go through the list.
Got it.
Now, before we get into the specifics, it might be helpful to introduce two more pointers, just to help us manage the boundaries of the section we're reversing. We can call them tail and con.
More pointers. Okay, I'm trying to keep up. What do these two do?
So tail is going to mark the beginning of the section we're reversing, and con is going to point to the node before tail. So they're like anchors, making sure that reversed section gets stitched back into the original list correctly.
Okay, so tail points to the first node that we want to reverse. And con is like its predecessor, the last node before the reversal zone.
Right.
So now we have 5 pointers in play.
Right.
I have to admit, this is where my brain starts to get a little overloaded.
I know, it's a lot to keep track of, but once we break it down step by step, you'll see it's really just about methodically updating these pointers.
Okay, I'm ready to dive into those steps.
Mm.
What happens after we've set up all these pointers? How do we start the actual reversal?
Okay, so first, we move cur forward until it reaches tail. Remember, that's our starting point. And as we move cur, we also want to keep track of con, which should always be one step behind.
So it's like we're setting the stage, getting our workers in the right positions before the main action begins.
Exactly.
Okay.
Once cur gets to tail, we're ready to start the reversal loop. This is where the magic happens.
Okay, I'm all ears. Walk me through those pointer swaps.
All right. So for every step in the section we want to reverse, we're going to do a few things. First, we store the node after cur in third, so we don't lose it.
Okay.
Then we make cur point to prev, so we're reversing that link. Then we move prev forward to where cur is and cur forward to where third is. Finally, we move third ahead one step to get ready for the next iteration.
Okay, wow, that's a lot of steps. But if I'm picturing it right, it's like we're meticulously shifting these pointers one by one, changing the connections as we go.
Yeah.
And that's what ultimately reverses the order within that section.
Yes, you got it. That's the heart of the algorithm.
That's impressive. But we're not quite done yet, right? We still have to connect this reverse section back into the main list. That's where con and tail come in.
Exactly. They're like our anchors.
Right.
So we make con point to prev, connecting the part before the reverse section to the new head of the reverse section. And then we make tail point to cur, which connects the tail of the reverse section to the part that comes after it. And boom, our in-place reversal is done.
That's amazing. We've spliced that reverse section back in seamlessly without needing any extra storage space.
Right. Pretty neat.
I'm pretty impressed.
Yeah,
This technique is so clever.
it really is.
But I do have one question. What if the section we're trying to reverse is at the very beginning of the list, where there's no node before it? How do we handle that?
That's a great question. We need to think about these edge cases, definitely.
Right.
If left happens to be 1, meaning we're reversing from the very start, we need to make sure our algorithm updates the head of the list to point to that new beginning of the reverse section.
So we need a special check for that scenario.
Yeah.
Are there any other potential pitfalls we should watch out for?
Another one is what happens if left and right are the same? That basically means we're reversing a section with just one node. In that case, we can just skip the whole reversal and return the original list.
It's like those tricky math problems where you have to watch out for zeros. We need to make sure our algorithm can handle those weird cases.
Exactly. It's all about thinking through the different possibilities and making sure the logic is solid.
Okay, this in-place reversal is definitely more complex than the brute force approach. But it's so much of it in terms of memory.
Right.
I'm ready to see some code.
Yeah.
But before we do, there's one more approach to this problem that I think is worth discussing. Recursion.
Oh, yeah.
Have you ever used recursion for linked list problems?
Yeah, I've played around with it, but to be honest, it still kind of makes my head spin. It feels magical, but I struggle to picture what's happening behind the scenes. Can we actually use it for this linked list reversal problem? Recursion can be a really powerful tool, especially for problems that you can break down into smaller, self-similar subproblems.
Okay.
And this linked list reversal, it fits that description perfectly.
Okay, you've got my attention.
Ugh.
How would we even start to think about this problem recursively?
Okay, imagine a function that takes the head of the list, left and right, as input. The base case, the point where we stop, is when we get to that right index. At that point, we just return the current node because that's going to be the new head of our reversed section.
Makes sense. So if we're not at the base case, we need to make a recursive call, right? But what do we pass to that call?
Right. We call the function again, but this time we pass in the next node and increase our current position. So basically, we're moving one step closer to right.
So with each call, we're going down the list, getting closer to our target. But how do we actually reverse the links as we go?
That's the cool part about recursion. As these calls return, they're actually returning the already reversed portions. We can store this reverse tail in a variable, let's call it new tail.
So new tail is like a chain of reverse nodes getting passed back up through the calls.
Exactly. And the trick is to connect our current node's next pointer to new tail. So we're adding it to that reverse chain. Then we return new tail, passing the reverse section up the line.
So we're building the reverse list from the bottom up, one node at a time.
Yeah, pretty much.
That's mind-bending, but also really cool.
It is. It's kind of beautiful.
So eventually, the very first call to our function will return the head of the fully reversed section, and we can connect that back to the original list using archon and tail.
Exactly.
Okay, I'm starting to see how recursion could work for this. It's a totally different way of thinking about it than the iterative approach. But it seems like it could be just as effective.
Definitely. But like with any recursive solution, we have to watch out for stack overflow.
Right.
If the list is super long, all those function calls can eat up a lot of memory.
So we're back to that memory trade-off.
Yep.
It seems like there's no perfect solution when it comes to algorithms.
You're right. It depends. Sometimes a simpler brute force method is good enough. Other times, a clever in-place algorithm is the way to go. And sometimes the beauty of recursion wins out as long as we remember about that potential memory issue.
This has been a really interesting discussion. We've explored a few different ways to tackle this reversal problem, each with its own pluses and minuses. I'm feeling a lot more confident about how to handle this type of challenge now.
Great. I'm glad to hear that.
But before we go any further, I have another question. We've been talking about how to reverse a section of a singly linked list where we can only go forward. What if we had a doubly linked list where each node has pointers to both the next and the previous node?
Ooh, that's interesting. That definitely adds another layer of complexity, doesn't it?
It does. Would those backwards pointers make things easier, or would it create new problems? That's something for everyone to think about as we move into the next part of our deep dive. Consider how being able to move back and forth might change our algorithms, both brute force and in place.
Yeah, that's a really interesting point to think about. And it kind of leads us to another important concept when we're analyzing algorithms, time complexity.
Time complexity. I've heard the term, but could use a refresher.
Mhm.
How does that relate to our linked list problem?
Okay, well, time complexity basically tells us how the runtime of an algorithm changes as the input size grows. So in this case, our input size is the length of the linked list.
So if we have a really long list, a less efficient algorithm is going to take a lot longer to run.
Exactly. That's why it's so important to understand time complexity when we're designing algorithms. We want our code to be as efficient as possible, especially when we're dealing with large data sets.
Okay, that makes sense.
Yeah.
But how do we actually figure out the time complexity of an algorithm? It seems like it could get pretty complicated.
Yeah, it can. But we usually try to focus on the big picture instead of getting lost in the details. We use something called big O notation to express this.
Big O notation. I've seen that before, yeah.
Yeah.
Involves things like ON and ON squared, right?
Exactly. So let's look at it in the context of our linked list problem. Remember that brute force approach where we copied the sublist into an array, reversed it, and then copied it back?
Yeah, the one that used extra memory?
Right. In that approach, we had to go through the sublist 3 times. Once to copy it into the array, once to reverse the array, and then once to copy it back. Each of these iterations takes time that's proportional to the length of the sublist.
So the longer the sublist, the longer each of those steps takes.
Exactly. Which means that the runtime of the brute force approach increases linearly with the size of the sublist. We express that using big O notation as ON, where N is the length of the sublist.
Okay, so ON means linear time complexity. What about the in-place reversal using pointers? What's its time complexity?
The in-place method is also ON. Even though we're being clever with pointers, we're basically still visiting each node once to change those connections.
So both methods have the same time complexity, even though the in-place method is much better when it comes to memory.
You got it. That's why we need to think about both time complexity and space complexity when we're evaluating algorithms. Sometimes there's a trade-off.
This is starting to make a lot more sense now. Big O notation helps us see how an algorithm's performance changes as the input gets bigger. And we have to look at both time and space to get the full picture.
Exactly. It's all about balance. Finding the right balance between efficiency and how much resources we use.
Okay, I think we have a pretty good grasp on time and space complexity now. But I want to shift gears a bit and talk about how we would actually code these algorithms. We've been discussing them conceptually, but I'm curious about your thoughts on how we would implement something like the in-place reversal in actual code.
Okay, yeah, that's a great next step. Turning these ideas into code is where it gets real. For the in-place reversal, we could represent our linked list using a simple node structure.
A node structure. Can you explain what that is?
Sure, a node is like the building block of a linked list. It usually has two parts. One is called data. That's the actual value that's stored in the node. Remember, we said the values could be between -500 and 500, so data would be an integer.
Right.
And the second part is next. That's a pointer that points to the next node in the list.
So each node is holding a value and a link to the next node, and that creates the chain.
Exactly. And the last node in the list, its next pointer is set to null. That tells us we've reached the end.
Okay, I can picture that. So how would we use these nodes to actually implement the in-place reversal algorithm?
Well, first, we'd define that node structure in our code. Then we could write our in-place reversal function. It would take the head of the linked list, the left index, and the right index as input.
And inside that function, that's where we'd start manipulating our prev, cur, and third pointers, right?
Exactly. We'd first check for those edge cases we talked about. What if the list is empty or left is the same as right? If either of those is true, we just return the original head of the list.
Makes sense. Those are our quick exits if no reversal is needed.
Right. If we get past those checks, then we move on to the core logic. We initialize those pointers, like we discussed earlier. Prev starts as null, cur starts at the head of the list, tail starts at the left node, and con starts as null.
Okay, and then we'd have to move cur forward until it reaches tail, keeping track of con as we go.
Right. We can use a simple loop for that. Something like, while cur is not equal to tail as, set con to cur and move cur to the next node.
That loop gets cur to the right spot at tail and sets con to the node right before it goes. Perfect. Now we're ready for that main reversal loop.
Exactly. Now we'd have another loop. This one runs from left to right. And inside this loop, we do those pointer swaps that we talked about using the third pointer.
The uncoupling and recoupling steps. Can you walk me through that loop?
Sure, it would look something like this. For each position from left to right, set third to cur dot next a, then set cur dot next to prev a, then set prev to cur, and finally set cur to third.
Okay, that's the core of it.
Yeah.
And after this loop finishes, we just need to connect that reversed section back into the main list using con and tail.
Right. The final steps would be set con dot next to prev and set tail dot next to cur.
And then we just return the head of the list, which will now have that reversed section.
Yep, that's it. The in-place reversal algorithm.
Now, wow, it's really neat how those pointer steps translate into code. It's pretty amazing how we can accomplish something so complex with a clear set of steps.
That's the beauty of algorithms. They allow us to break down these tricky problems in a systematic and efficient way.
This has been such a great look into linked list reversal. We've seen different approaches, analyzed their complexities, and even went through the logic for an in-place reversal implementation.
Yeah, it's been a really good overview.
But before we move on, I have a question that I think a lot of people new to linked lists might have. Why even use them? Aren't arrays just easier?
That's a fair question. Arrays and linked lists are both really important data structures, each with their own strengths and weaknesses. Arrays let you access elements directly using their index, which can be very efficient. But they have a fixed size. You have to know ahead of time how many elements you'll need.
And if you need to add or remove elements from the middle of an array, that can take a long time, because you might have to shift a lot of elements around.
Exactly. Linked lists, on the other hand, are dynamic. You can easily add or remove elements from anywhere in the list without having to shift other elements. This makes them great for when you don't know how much data you'll have or if the size changes a lot.
So linked lists are more flexible when it comes to adding and removing elements. And arrays are more efficient for direct access.
You got it. And there's also memory allocation to consider. Arrays are usually stored in one continuous block of memory, which can be a problem if you need a really big array and there isn't enough space.
But linked lists don't have that problem, since the nodes can be spread out in memory connected by those pointers.
Exactly. So which one you choose, arrays or linked lists, really depends on the problem you're trying to solve.
That makes a lot of sense. It's about choosing the right tool for the job, understanding what each data structure is good at.
Absolutely. And once you understand linked lists and how to work with them, it opens up so many possibilities in algorithm design.
Okay, I think we've covered a lot today on linked lists and how to reverse them, but I want to go back to something we mentioned earlier, recursion. We said it can be really elegant, but sometimes uses a lot of memory. I'd love to dive a little deeper into what a recursive solution would look like in pseudocode.
Sure, let's do that. Just like with the iterative approach, our recursive function would take the head of the linked list left and right as input.
And the base case is when we hit the right index, right? That's where we stop.
Exactly. Our base case would check if our current position, which we're tracking in the function, is equal to right. If it is, then we've reached the end of the section we want to reverse, and we just return the current node.
That makes sense.
Yeah.
The current node would be the new head of the reverse section.
Right, but if we're not at the base case, meaning our current position is less than right, we need to make that recursive call. We call the function again, this time passing in the next node and moving our current position one step closer to right.
So we keep calling the function, going down the list, getting closer to right each time.
Exactly, and this is where the magic of recursion comes in. As those recursive calls return, they're actually giving us the reversed portions of the list. We can store this reverse tail in a variable, let's call it new tail.
Okay, so new tail represents the head of what's already been reversed.
Exactly. Now, here's the key. We connect our current node's next pointer to new tail. So now the current node is part of the reversed section.
That's how we build the reverse list as we go. So
Yeah.
we make the connection, and then what do we return?
We return new tail because that's now the head of the reversed part that includes the current node.
I see. So each call gets the reverse tail from the calls below it, connects its node, and returns the updated tail. It's like a domino effect.
You got it. And finally, the very first call to the function will give us the head of the entire reversed section, and we can connect that back into the original list using our con and tail pointers, just like in the iterative method.
Okay, my mind is a little blown, but I think I'm starting to get the beauty of recursion. It's amazing how we can break down this complex problem into these smaller, self-similar steps.
That's the power of recursion. It often gives us very clean and elegant code, even for complicated problems.
But we still have to be careful about that potential memory overhead.
Definitely recursion is powerful, but it's not always the best choice. If we're worried about memory, it might not be the way to go.
This has been such a great dive into linked list reversal. We've explored both the iterative and recursive approaches in detail. We've covered a lot of ground, and we've even looked at the pseudocode for these algorithms. But I want to zoom out a little bit and talk about the bigger picture. What are some real-world situations where we would use linked list reversal?
That's a great question. Linked lists and all the ways we can manipulate them are used in a lot of different areas. One common one is underrated functionality in software. Think about a text editor or a drawing program. You can undo and redo actions.
So each action you take could be like a node in a linked list. Undoing or redoing would be like going back and forth in that list, maybe even reversing parts of it.
Exactly. Another one is browser history. Your browsing history is basically a linked list of the pages you've visited. The back and forward buttons let you move through that list.
That makes sense. And I bet linked lists could also be used in music players to manage playlists, or in image editing software to store layers.
Absolutely. And they're also used a lot in operating systems for things like memory management and scheduling processes.
Wow, linked lists are really fundamental. They're used all over the place in our digital lives.
For sure. Understanding how to use them is super important for any programmer.
Okay, I think we've really explored linked list reversal and its applications. But before we finish this part, I want to touch on one more thing. The idea of in-place algorithms. We've been using that term a lot, but I want to make sure everyone really understands what it means and why it's important.
Definitely, it's worth clarifying. We've talked about how in-place algorithms, like our pointer-based reversal method, change the original linked list directly without making a new one. But why is that better? Why not just create a new list with the reversed section?
That's what I always wondered. What's the big deal about doing everything in place?
The big deal is efficiency, especially when it comes to memory. Creating a new linked list means you need to allocate new memory for every node in the reversed section. And that can be very costly, especially for large lists.
Ah, so by changing the original list directly, we're basically reusing the memory we already have. That saves space and probably time, too.
Exactly. It's like rearranging the furniture in a room instead of going out and buying all new furniture. You're working with what you have, being efficient.
That's a great way to put it. It finally makes sense why in place is so desirable.
It's a really important concept to understand, especially as you learn more about algorithm design and optimization. Being able to work with data structures efficiently, both in time and space, is what makes a good programmer.
Okay, I think we've covered just about everything on linked list reversal. We've looked at different ways to do it, talked about their complexities, went through the pseudocode, and even explored real-world uses and why in place is so important.
It's been a really deep dive.
But before we move on to the last part of our episode, I want to leave everyone with one final thought. We've been talking about reversing a section of a linked list. What if we wanted to rotate a section of a list by a certain number of positions? For example, if we have the list 1, 2, 3, 4, 5, and we want to rotate the section from position 2 to 4 by 2 positions to the right, we would end up with 1, 4, 5, 2, 3.
Ooh, that's a good challenge. It builds on everything we've talked about today and makes you think about pointer manipulation in a slightly different way.
Exactly. It's a great way to put your new knowledge to the test.
I encourage everyone to give it a try. And remember, the key to getting good at working with linked lists is practice and trying new things.
Well said. So we'll leave everyone with that challenge for now. Thanks for joining us on this deep dive into linked list reversal. See you in the next part.
Yeah, it's been a pretty deep dive into the details of linked lists and how to work with them. Hopefully, everyone's feeling more confident about tackling these kinds of problems now.
I think so too. But, even after all this, I still feel like we've just scratched the surface of what linked lists can do. We focused a lot on this one problem, reversing a section. But there's a whole world of linked list algorithms out there.
You're absolutely right. There's a ton more to explore beyond just reversal. In fact, some of the most interesting and toughest problems come up when you combine linked lists with other data structures and algorithms.
Okay, now I'm really curious. Can you give me an example of one of those more advanced linked list problems?
Sure. One classic example is merging two sorted linked lists. Imagine you have two linked lists, each one already sorted in ascending order.
Hmm.
The goal is to combine them into one single sorted linked list efficiently.
That sounds tricky. It's like having two lines of people, each lined up by height, and you have to merge them into one line, still sorted by height, without messing anything up.
Exactly. And you want to do it as efficiently as possible, ideally going through each list only once. It involves comparing the values at the heads of the two lists, picking the smaller one, adding it to the new merged list, and then moving the pointer of the list you took it from.
Okay, yeah, I can see how that would work. And you're basically weaving the two lists together, checking the values as you go to make sure everything stays sorted.
Exactly. And the cool thing is you can do this really nicely using recursion or iteration.
That's one example.
Yeah.
What other kinds of challenges are there with linked lists?
Another interesting one is detecting a cycle in a linked list. Imagine a linked list where the last node, instead of pointing to null, points back to an earlier node in the list.
So it's not a straight line anymore, it's a loop. I can see how that could be a problem if you're trying to go through the list. You could get stuck going around forever.
Exactly. So the problem is to figure out if there's a cycle in a given linked list.
How would you even do that? It seems like you could just keep going and going if there's a cycle.
Right. That's the tricky part. There are these clever algorithms that use two pointers that move through the list at different speeds. If those pointers ever meet, it means there's a cycle. It's a really cool example of how a simple idea can solve a pretty complex problem.
Wow, that's really neat. It's like a race between the pointers, and if the faster one catches up, you know something's wrong. I definitely want to learn more about that.
You should, and there are lots of other fascinating problems with linked lists. Finding the middle nodes, splitting the list around a specific value, removing duplicates. The possibilities are endless.
You've convinced me I need to spend some time exploring these more advanced linked list problems.
I think you'll enjoy it. Linked lists might seem simple at first, but they can lead to some really interesting algorithmic challenges.
Well, on that note of branching out and taking on new challenges, I think it's time to wrap up this deep dive. It's been an amazing journey into the world of linked list reversal, and I feel like we've all learned a lot today.
Definitely. We've covered so much, from the basics to some more advanced stuff.
And the biggest takeaway for me is that to really master linked lists or any data structure, you need to practice, experiment, and be willing to really dig deep.
Absolutely. To all our listeners out there, keep exploring those linked lists. Try those tricky problems, experiment with different approaches, and don't be afraid to get your hands dirty with some code.
And remember, the process of learning is just as important as the end result. Enjoy the challenges, celebrate the breakthroughs, and never stop exploring this amazing world of algorithms and data structures.
Couldn't have said it better myself. Thanks for joining us on this deep dive into linked list reversal, everyone.
Until next time, happy coding.